Okay, that's agreed. So I will go to the slides, but I want us to start with the geometric idea behind linear discriminant analysis. So today we shall be looking at this linear discriminant analysis. Let's try to look at the logic behind it. So it has two things it tries to do. It tries to do some classification. Reduction. The two things. Some kind of supervised dimensionality reduction. So how does it work? So we'll look at maybe the simplest case, where you have only 2 dimensions initially. This can be more than 2, but for simplicity, we can work with 2 dimensions. Suppose you have, so suppose I have some data points here. Let me just put a circle here to cover these data points, since drawing the dots takes long. So I'll just say now there's another cloud of data points here, right? Maybe that might not serve intended purpose well. So suppose the other class is somewhere here. So these are all points. I'm just drawing a boundary to so that it's easier for you to see everything. So the aim is the following. You know that these 2 groups, they are classified. So maybe this is group 1 and this is group 2. And you have these 2 measurements, X and Y, measured on those 2 groups. Now you want to find a way of classifying into one of these 2 groups, either group 1 or group 2, based on these 2 measurements. So if you apply something like, although for a 2-dimensional case, PCA sometimes is not
Excuse me,
not make a lot of sense. But if you are to think in terms of PCA, PCA will may not be able to separate the 2 classes once you visualize, because all it does is looks for directions of maximum variance and doesn't look for. Yes.
There are some students requesting you admit them.
Admitted them. So PCA simply looks for directions of maximum variation. It doesn't try to separate the data. So, but what linear discriminant analysis will do now, it will try to look for a plane. So for instance, if you draw a plane here and you project this data onto this plane, so like this red data, if you project all the points, they will all just be held within this point. And then if you project this one down here, all the blue points will just be between these 2. So this sort of gives you a separation between these 2 clusters. And if you get any new points and project it and it lands within this region, you can classify it as being in group 2, or if it lands in the other region, you can classify it as being in group 1. But you can go further and actually compute the probabilities. There are some additional things you can do where you use the priors and the posterior probabilities to compute the probability of a certain point being a member of one of those groups. So I will not go through the probability way of solving this. We just stick to the linear algebra. So this vector is what LDA does is try to look for this vector, which maximizes the separation between the means or the averages of the two. It maximizes that separation and then tries to minimize the variation within each group. So if the variation within each group is small, then it's easier to classify them. But if a distance between, and also it's easier when the distance between their means is also higher. So linear discriminant tries to find this plane that separates the groups as much as possible. So it maximizes the between variation and minimizes the within variation for the different groups. But it is supervised because you already have labels for your data. Unlike PCA, PCA does not, you don't need labels to run PCA. You can use the labels to check if PCA has found the groups, but you generally don't need labels for PCA. So that's the basic idea behind linear discriminant analysis. Many times you'll work with more than two variables, more than just two variables. So you will need some analytical way of understanding it. So maybe we can try to look at that. So the other thing you will, the reason we said it's dimensionality reduction is like, for instance, in this case, what has happened is that we reduce our space to just this one-dimensional space, which is a line onto which you project. Initially, we started with two, but now this one-dimensional space will give us the separation we need. So, for instance, if you had a line going this way, this one does not, because you can see there's some intersection there. If you drop along that line, there'll be some intersection. But LDA will try to find this best line that separates the two classes, and then you're able to classify them based on some probabilities. You're able to compute the probability of being in either class. So the one that has a higher probability is where it is classified. It's also possible to start from using those priors and posteriors to show how you end up at the equivalent. You can work from the probability side and you'll end up here. You can work from the linear algebra side and you still end up with the same result. So this other one for the probability side involves a lot of calculations that don't have a lot of linear algebra. But the focus of this course is more linear algebra than the probability and statistics. So the details of this you will learn in the other machine learning courses. If you want to go approach it from the probability side, here our focus is to see where linear algebra fits in. I think also if I happen to teach, there's a course for optimization. Which is in the second semester. If I teach that, then we can now cover this in more detail and show how you arrive at the optimization.
Okay. Think lakini iko na discount.
Whose microphone is on? I don't know who it is.
Ingine bado itaongezea usiwari.
James Research. Let's see if we can mute him. I've disabled his mic. He's probably not in class. Amewasha tu akatoroka. So, people still coming in. So that's the basic idea. You try to look for a plane. In this case, we look for a line that maximizes the separation between the two classes. And then you're able to classify a new point as belonging to one of the classes. It can do for more than two classes. I just gave an example where you have two classes. So let's go to the so this one I've already explained. What LDA does is it's tries to do some classification and also dimensionality reduction. So you want to find a lower dimensional space which maximizes separation between the two classes. In our case, we moved from two-dimensional to one-dimensional, the example that we did. So here, what this shows is the optimization process. So what you'll be doing is basically the following. There's this variation, this covariance matrix, so the estimate of a covariance matrix of the between the classes. Hey, what is happening? Something is not right. Yeah, now they are moving. I think I need to close this. No, but I will need it. I think this one for pencil spaces is the one that's eating up memory. Takes up quite a bit of memory, so I'll close this because I don't need it now. Hopefully that will make what's going on. For some reason, the slides are not moving. That's why I am, or rather, they are not moving when I press the arrow keys.
I think your cursor is a hand, so you have to deselect that from the PDF.
No, the cursor is working. It's a keyboard that is not working. So I'll use the cursor. Yeah, see, the cursor is able to go all the way back, but when I use the keyboard, for some reason, it's not moving the slides. So LDA does this. It classifies and tries to reduce the dimension as well. So what usually you are supposed to do is to minimize this quantity. So you find a vector onto which you can project and minimize within. What do you call it? You maximize separation between the classes and minimize the variance within the classes. And this is what you try to, this is your optimization objective function. I will not focus so much on this for now, but basically it's this: if you maximize the between cluster scatter matrix, it means it's easier for you to, if you maximize a between group variation, it's easier for you to classify. And if you minimize the within class variation, your classification is more accurate. So this is how you compute the within cluster matrix if you have about C classes. C here counts the number of classes. In the previous example, we had only 2 classes. So this gives you the formula for computing the within cluster. It's just a covariance matrix. And then this is a between cluster covariance matrix. So this is the one this variance is the one you try to minimize, maximize. So this between you maximize, and this is the one you try to minimize. And the objective function that we have seen before is what will give you this. This W is just the vector onto which you'll project your data and maximize the separation. So luckily there is a solution to this problem that is simple. Once you have these 2 matrices, you can find a solution as follows. There's the inverse of the within cluster matrix and the between multiplied by the between cluster matrix. So this product, once you have it, you will look for the eigenvectors, right? So your solution is to find the eigenvectors of this matrix, the product of these 2 matrices. So once you find the eigenvectors, you have gotten the eigenvectors that onto which if you project, or the subspace generated by those eigenvectors, onto which if you project your data, you'll maximize the separation between the classes and minimize the variation within each cluster and makes it easier to classify. So this sort of gives a list of the steps that are involved in LDA. The first thing you do is compute the mean for each class and the overall mean. Then using those, you can compute the within cluster variation matrix and the between cluster matrix as we gave a formula earlier. Then we solve that eigenvalue problem. I can go back so that this is the eigenvalue problem, where we find the eigenvalues and eigenvectors matrix, the product of the inverse of the within scatter matrix and the between scatter matrix. So these 2, the product, you just do the eigen decomposition, find your eigenvalues and eigenvectors. Then after you find the eigenvectors, you can pick the top k eigenvectors. Now these top k eigenvectors will generate a subspace, and you try to project your data onto that subspace, and then able to separate your data better because it will have maximized the separation between the classes and minimize the variation within each class. So you make the groups closer and separate their means. Then you're able to find the class, classify better. So this just repeats what I was saying. So as an example, we can apply it to this credit risk modeling as follows. So we shall go and do an actual example in Python, but let's try to describe it first. So if you have features like income, debt ratio, and credit score, you can use LDA to group borrowers into low risk and high risk. So for instance, you could consider low risk borrowers to be those with high income and low debt ratio, and the high risk borrowers who are unlikely to pay back the loan with a low income and high debt ratio. So if you have all this data on the individuals, you'll be able to predict whether they are creditworthy. So I think this is the other things it does as well. It can pull out the feature importance. The coefficient of the linear discriminants also can give you the feature importance, but I will not focus so much on this. we can plot them in 2 dimensions so that we visualize the separation. I think that was it for the explanation. Maybe I will try to put in more detail on that is between this part and this part, or maybe pick an example and run through this. You can follow. If you do a 2-dimensional example, then it's easier to see. So I think I'll try to do that later. Today, my afternoon was derailed. I had all these big plans, but to finish up the details, but I was delayed. So that's basically the idea. So we're going to run this in, we will not run it from scratch. We'll just use the functions that are inbuilt in Python. But it would be an interesting project to try and program this from scratch, because you know exactly what is needed. So I have the file here. So I don't know if you can see my. So we shall generate some, we'll simulate some data, and then we use that data to demonstrate the concept of linear discriminant analysis. So there are all these libraries that you need. You need the NumPy, Pandas, sklearn. You need a model selection, which splits the data into training and testing. You have the linear discriminant analysis. Again, these classification reports and receive operating characteristic and so on, AUC score. You will learn those in machine learning. Maybe that we shall do at this point is look at the confusion issue is just to see where linear algebra works. The rest, you have all these other courses you're doing. It will show you that. So the first thing we do is to set up around the seed so that we can reproduce the data. We want only 200 samples. You can increase that if you wish when you're running this. Variables. We generate some income variables, normally distributed with mean 50,000 and standard deviation 10,000. And we'll exact of them, n samples here. So the data 0.1 and 0.5. So this gives debt to income ratio, and we generate 200 such random values. And then the credit score will generate random normal values with mean 700 and standard deviation of 50. And again, only 200 of them. So all these will be our variables. We'll have income, the debt ratio, and the credit score. So the next thing we do is we create the low risk and high risk customers. We label the low risk. So we use some criteria to so this will which gives us a value of 1 for, or true, if you like, for the low the risky customers. So high risk will be 1. So all this, if any one of them is met, if the income is less than 45,000, credit score is less than 650, and debt ratio is greater than 0.4. If any one of these conditions is met, that the given row in this the data frame will be classified as high risk if any one of these three conditions is met. Otherwise, the other ones who are low risk will be labeled 0. So since this first one will just give you true false values, we can turn them into integers so that we have ones and zeros. This second, this line does here. So this first one will give you true and false values, but we want them to be that, I suppose. All this is put variables, a variable that specifies whether a customer is risky or not. Put them into a data frame. Then we split into the features and the target variable into. But now I think you have done the process. You must have an idea of what training and testing set is. So this is our data frame. We have the income, we have the debt ratio, we have a credit score, and this is the variable showing whether it's risky to lend them or not. High risk or low risk. So high risk is one, low risk customer, and more likely to be back here. Will be high risk or low risk. That's the plan. So we'll initialize this LDA object and we feed it on the training data. Then we predict on the test set and then give the abilities of being in a given class here. So you need this for this operation characteristic, but we shall not this AUC score. We shall not the area. But in your own time, you can look at those.
Excuse me.
Based on what you do in the other classes. So basically, this is all you need. These two lines. This instantiates the LD object, then you feed it on the training data, and then you can predict it on the test set.
Is your screen?
And that's it. With that, you can create the confusion matrix, and you'll be able to see the accuracy. The accuracy in this case was it gives some additional things. About 79% accuracy. You can check that. Just add 8 plus 30 and divide test set. So what was the proportion we gave? 0.3. So 0.3 took 60.
Excuse me, sir.
260. So 18 plus 48 out of 60. Accuracy. Someone trying to speak?
Yes, I was trying to speak before. I could. Can you hear? Can you hear me?
Yes, I can hear someone speaking.
Okay. First of all, there's some people wanting to be let in, and second, I think I cannot. You keep breaking up, and your screen is stuck on a different cell on the notebook. I don't think what you're explaining is on the same screen.
So what can you see now on the screen?
So I see the first cell, which was where we were generating deciding whether something is a risk or not, based on the income, credit score, and debt ratio. I don't know if it's just myself or
So if I move it like this, can you see it moving?
nothing is moving. I think it's stuck. It's been stuck.
I've moved it now. What can you see on the screen as a top? Pardon?
The same thing. We want the same. Oh, okay. Now it's moving.
So the same problem, or
Is this so? It just moved slightly, but I guess. And then, oh, but before I forget, there are some people who wanted to be let in. I don't know if you let them in.
what are you pending in the group? So now I don't know who is is there anyone else was not able to follow when I was moving the script?
Yes, you're breaking
your
quite a lot.
script was not moving.
No.
Also, you are breaking
Try
quite
something
a
else
lot.
here and see. Let me try the
Hello. Yes.
now. Seem to be tough. You can hear me?
Can hear you now. But you still seems like your voice is still breaking. Can you hear us?
Quite clearly, but for some reason, I don't know what's wrong with my connection on my end. No. You can't hear me, or
I can hear you, but it keeps disappearing, I guess.
it's still disappearing up to now.
Now it seems a bit clearer. Let's see if it goes on.
So what we do? Do I start the script again?
We could do that.
You start the class.
Yeah. Well. The class again. Okay. To reconnect this again. Okay, give it a minute. We will start shortly. Although if you see the connection is bad, you should speak up early. Don't wait until it's.
I'm wondering if the recording is still on. You probably can also confirm that.
Stop until I stop it. Even if I'm kicked out, it continues recording.
Okay.
So if you continue talking about me when I'm not in the class, it will just record now. But nyinyi hamkuongea, sijui muliogopa kuongea, mungeongea tu when I was out. Okay, let me share the screen now. I was setting up the board. So, we start afresh. We are working on linear discriminant analysis, usually abbreviated as LDA. So what linear discriminant analysis is, it tries to separate, it tries to classify. It does two things. One, all these can be illustrated with some mathematics, but for now, I'm focused on the basic idea, just the concept behind it. It tries to classify. And also it tries to reduce dimension. For example, you can work with a situation where you have only two variables. So suppose you have some measurements on some subjects. You have only two variables, X and Y. It may turn out that you have two groups with different characteristics. And they are labeled. The groups must be labeled in this case. So big lines are just enclosing a set of points. I think it's easier for me to draw it that way. So the lines just enclose a set of points. So you have several points in here. So it's easier for me to draw them like that than to, or faster for me to draw them like that than to draw them point by point. Oh, I've deleted Let's undo. Good. So we have two sets of points, and each of them is known. Their classification is known. So this might be a group which we label 1. So we know this beforehand. That they classified, but we don't know whether we can separate them properly. But we have some measurements. So we have these measurements on those individuals, and then we want to see if we can use these measurements to determine whether they belong to this class or that class. So what LDA does is the following. It will try to look for a plane, in this case a line, since we are from 2 dimensions. If you go down 1 dimension, you draw a line. If you're in 3 dimensions, it would be looking for a plane. So you're looking for a plane which, after projecting the data, you project the data onto that plane. After projecting that data onto this plane, you're able to separate the classes quite well. So what it does here is it maximizes the distance between the means. So suppose this was the centroid or the mean, if you like. It maximizes that distance between the means and minimizes the variation within each cluster. So this variation, it tries to make it as small as possible. This variation within the cluster, it tries to make it as small as possible. And then you're able to classify a new point. If you get a new point, you'll be able to classify it by simply projecting it onto the new coordinates, the new space rather. Once you project it into the new space, you'll be able to compute the probability of that point being in one of those classes. So if it's higher for 2, you classify it in 2. If it's higher for 1, you classify it in group 1. So I will not go into the details of the probabilities, but you can actually arrive at the same conclusion just by starting from the working, assuming that these 2 are normally distribution, making some simplifying assumptions, and ending up with exactly the same idea. So basically what LDA does is to find this line. If you're working in 2 dimensions, it will find this line. So this line is the one that maximizes the separation between these 2 and minimize the variation within each cluster. So if the variation is smaller, the classification is more accurate. And also if the separation is bigger, the classification is more accurate. There are situations where it makes more sense to use LDA than, because the other thing you could use for this is a logistic regression, but there are situations where it makes more sense to use LDA. But I imagine you learn all these things in the machine learning classes. Now we'll focus on the linear algebra. So the main thing will be to find this. This is like your, let's call it W. This vector is what you're looking for, the one that will separate these 2 classes as much as possible and minimize the variation within each class so that your classification is better. So is that making sense? So this vector is the one we're trying to find. Now, if you're dealing with more than 2 dimensions, you may find more than one vector. There's W. Maybe this one does a separation in one direction. Then you look for the next one that does a separation in a different direction and so on. So if you have 3 dimensions initially, maybe you will be looking for a plane onto which you project the data. So maybe when you project the data onto the plane, that plane will give you the best separation between the clusters and minimize the variation within each cluster. Is that making sense? So ideally, if for instance, you try to use a different, so this would be the best line. This is the one you're looking for, and there are ways to find it. And if you have If you have more than 2 variables, then you'll be looking for more than one W. There'll be several Ws that you're looking for. The first one being the one that does the separation, better than the others. So there are other possible lines you can use, but they won't be as good as the one that LDA finds. So for instance, if you use this line to separate, if you drop this one down, project it onto this line and project, now you can see that there's still some intersection. The separation is not so good, but it was better when we used the line in that direction. Now, if we drop all the points and work with just that one dimension instead of a 2, our separation is better. So it keeps looking for these lines until it finds this one that does the separation. Well, if you are working in more than 3 dimensions, it will look for the subspace that is spanned by these several such lines or such vectors. So then you project the data onto that subspace, and that subspace is what will separate the groups and at the same time minimize the variation within each group. So if that is, I think, the best I can do in terms of a layman's, I think what one of you always says, a layman's explanation. So I'll try to run through the slides again to see if we can give this a better. Forget it, it's here. Full screen mode. So now we have this one simply repeats what I was saying in this in the slides. So there's nothing new there. But then there's a way you find those directions, these vectors W that minimize the variation within each class and maximize the variation between the classes. So you need to maximize this between cluster matrix, between class scatter matrix. It's just a covariance matrix, and within covariance matrix, within variation. Let's just call it within cluster matrix. Focus. The main thing is that it measures the variation within each cluster, which should be minimized, and SB measures the variation between the clusters, which should be maximized. So SW should be minimized, SB should be maximized. When projected to the new space made up of these Ws. So you find these Ws as eigenvectors. So this is how you compute the SW and SB. We had seen this earlier, I think. Those are the formulas where you have, here you assume you have C classes. The example we gave had only 2 classes. So here we assume we have exactly C classes. And this is how you compute the within scatter matrix and the between scatter matrix. So like I said, I will write out an example for a 2-dimensional case and compute these matrices and share later, so that this becomes clearer. As it is, some people may not understand what is in these formulas. But you can see these are all vectors. Xi is a vector. Mu k is a vector consisting of the means. So on. So, but we'll do a 2-dimensional case so that it can be clearer. I don't have it ready now. That's what I'll do. So now, to find these vectors W that help us to maximize the separation, we solve this problem. because this matrix, we shall have obtained it from the data, these two matrices, SW and SB. So this product of the inverse of SW and SB will give us a new matrix whose eigenvectors will be the vectors we are looking for. So these W's will just be the eigenvectors of this matrix, which is a product of the inverse of SW and SB. So we get as many of these vectors as necessary, W. And we form a matrix and try to project the data, each data point onto this new space. And in the new space now, the separation will be maximized. So we'll, instead of working with the original space, now we project it onto the new space. So like I said, I will illustrate this with a two-dimensional case. This, where am I going back again? So these are the steps involved. Now, if you get a new point to do the classification, you have there's some probability involved. Like I said, I don't want to. I will not go into the details of probability now. You can still hear me?
Yes.
Yes.
Something is not right about my keyboard. I think it's. Sometimes it works, sometimes it doesn't work. So the example we can work on is this credit risk modeling example, where you given some features like income, debt ratio, and credit score. You can be able to tell if a client is a low risk borrower or a high risk borrower. And the model will be fine. Into one of those classes. So we shall see, we shall use some visualization to see how it works. So the other thing, maybe I forgot, the decision boundary is also linear. So what will happen is, like in this case, a decision boundary will simply be the line that, this line that goes through here will be a linear decision boundary. So anything that falls on this side will be belonging to this class, and anything that falls on that class will be belonging, or on anything that falls on this side will be classified as belonging to this class. So it's not always the case that the separation is perfect. This one is just an ideal case which I have created, but many times you will have some points that there'll be some intersection in real life. So this is not always perfect. You might have some points that are misclassified. So that's what I'm saying. Or rather, some points that share common values, yet they are on either side of the classification. So the data we shall use is simulated. We need all these libraries. For this last one, I think the only thing we'll work with is a confusion matrix. The rest, like I said, I don't bother with them because these are things you're supposed to learn in the machine learning class in detail. So I will not delete them, but the focus will be on this one, the confusion matrix. That's the only thing we shall pull out. Then things like cross-validation, again, we don't focus on those in this class. You learn those in your machine learning classes. So here we have a random seed to make sure we can reproduce the same data. We generate the income as from the normal distribution with these parameters. We generate the debt to income ratio as proportions between 0.1 and 0.5 using the uniform distribution. Again, the normal distribution generates the credit score. So we have 200 measures for each of these variables. randomly generated. And then we set up some thresholds for high risk customers. So if the income is less than 45,000, we take that to be a high risk customer. If the credit score is less than 650, we take that to be a high risk customer. And also if a debt ratio is greater than 0.4, we consider that a high risk customer. So what this will do is will create a vector of the same length as these variables. And where any one of these conditions is satisfied, it will classify that as a high risk client. So it will label, it will give them the true value, and all the others that are given false will be considered low risk customers. But since this is a logical, it's Boolean, it will give us a true and false values. We want them as ones and zeros, so we convert it to integers in the next line. So you can print this later on to see the outcome. Print after you run this first risk, print it so that you can see it's actually only true and false values. But we prefer to label them as ones and zeros, so we convert that to integers. That's what the second line does. Then we put all that into this data frame using the pandas module. Then here you can preview the data. Here, this next one picks the features separately and the target separately. Then we split them into the training and testing sets. So this is the data itself. I think this is a command that produces that. So this is the data. You have the income, you have a debt ratio, you have a credit score, and then you have the classification of high risk or low risk. 1 for high risk and 0 for low risk customer. So what the aim now is to predict whether a customer is a high risk customer or low risk based on this information, these three variables. Can they help us to do that? Now, we will just make use of remember we imported this function or the object LDA. So we can instantiate it here. And then we can fit the training data using the model LDA. And we can make some predictions using the test set. That's all. So these three do all that work that you need to. Of course, there are some, you can make it more complicated if you wish, but this is all you need now. If you want to compute the probabilities of being in a particular class, this one will give you that. This line here, but I'm not interested in these probabilities. These ones you will do in the machine learning class. So once we have the predictions, we can create the confusion matrix. So this line gives us a confusion matrix. We have a test. They observed the actual labels, the true ground truth, and then the predicted labels for the test data. And it gives us about 48 correct predictions out of 60. Remember, we split the data into 30% test and 70% training. And we had 200, so 30% would be 60 points out of a 200. This shows the results of those 60 points. So 48 out of 60 is what? Is it 70%, 80%? Roughly. So the other issues you may consider in this kind of analysis, you have the class imbalance and so on, but that is not of interest now, because our focus is a linear algebra. So I'm running, okay, I need to connect the runtime. I think it's still connecting. So here is I've run that, and now we have the data. So the next one, I will run it, and it will produce our confusion matrix. And we can see what it does. So now, you can also plot onto the first two. Just use the first two variables and use the classifications given by the no, is this the let's check first. I can't remember what classification was here. These are just the predictions on the grid points. So these are just some new points. You set up the grid and then do predictions on those grid points, and then plot the predicted values and the classification. And then you color them using the ground truth. So this one just uses the two variables as they are, the raw variables, income and credit score, then colors them with the ground truth. I think that is the case. The actual values. Then when you do the projections, you can project onto the like this is the first component value. Basically, this is you project it onto this direction that maximizes separation. And when you do that, you can do some histograms of the data points after they've been projected onto the first component. If you do the histogram, you can see that now these blue ones, the blue represents what? Low risk is blue. So the low risk score lower values on the first component. They're mostly this blue. That's a histogram with blue, right? And then this other color, what was it? It's red. Doesn't look like red here, but so the red one now is the high risk. And you can see there's some sort of separation. Of course, there's some overlap in between here, but it seems to, in some sense, separate. In some way, separate the low risk and the high risk if you line them up along that first component. So you can also plot them separately. This one plots the two separately instead of putting them in one chart. So this is now projecting the data onto the first component or the first direction that separates the data. And you can see also the separation can be visible. You can see this one is mostly on the negative side. Most of the values are below 0. For this one, majority of the values are above 0. So it does some separation. You can also use a KDE plot. I think I used, here is this kernel density plot, which gives you a better picture. Of course, there's some overlap, but it separates the two classes fairly well on the first component. Then the rest, I think this was measuring the feature importance. Using those coefficients, you can figure out the feature importance. So it says the debt ratio is the one that contributes the most. The other two don't seem to contribute much. This credit score and income, they don't seem to contribute much to the to the prediction. But this is of no interest to us now. We're more interested in the maybe up to this point where you compute the projection on the first component or the first direction in which you project the data. So this basically has reduced 3 dimensions into 1 dimension. So you project everything onto this 1 dimension, and then you're able to see how well it has separated the two. So it doesn't always do a perfect separation, but it's reasonable. So this last one just draws the decision boundary. It picks some 2 variables. This is in 3D, but so in 2D, this one gives a decision boundary. For these 2 variables, if you have income and debt ratio, it's able to draw the decision boundary. So anything on this, on the lower side of that boundary would be classified as what was blue for? I keep forgetting. So blue is blue is low risk and red is high risk. Yeah, pardon. So this covers the decision boundary, and you have the. You can, if you get any new point, you can classify it. But this now is not projected to the components. We've just used the actual variables, income and debt ratio, and produce a decision boundary. There's a lot of code there that does that for you. So this one, we are not interested, but it gives a feature importance, and it tells you the debt ratio is the biggest contributor. Our stopping point was supposed to be here, where we see how the first component separates the data. So I'll stop there for today. I will share with you the example for the 2-dimensional case, which is numerically worked out. Then you'll be able to follow. There's also a lot of videos online. Some of them a bit technical, some a bit too simple, that can help you understand what's going on. Or some actually do this and approach it from the probability direction. You end up at the same spot. Doesn't matter which direction you pick. So now what you can do, you could look for some data. I think there's some there's a lot of data on credit risk that may have more than 3 variables. So you can try to apply this to a larger a data set that has more. I can also look for a data set and share. I think there are quite a number of data sets available online, publicly available on this. I can share one where you can attempt to apply the same and see how well it does the classification, and probably do these histograms to see how the separation is good or not good. Okay, so I'll stop there for today. Unfortunately, I didn't have the worked out example because I got my plan today went off completely. I thought I had enough time. Things did not go my way. Are you still in class? In the code to make it more easier to explain, easier to understand. So next time you download the link, I think you'll find some more comments. So I've shared the link in the chat. You can try to run it on your own. Maybe I can go back to the most important bit. So that you understand what's going on. So like I said, I think a lot of the other things are not so important. The most important bit that helps you to fit. This first one, we generated the data, but I think for your case, maybe you will find a case where the data is already generated. Rather, the data is already collected. So the first thing you probably will do is to split it into the features and the target, and then split into training and testing. So this is a fact. Once you have the data, you do this to the data. You pull out the features, the numerical features, and pull out the target or the labels into separate data, then split the data into training and testing set. You can determine what your test size will be. If you want 20%, you can change this to 0.2 instead of 0.3. Then this second block is now all you need to run LDA. It gives you a confusion matrix. If you want the extra data, it's also available. The area under curve score is 0.85. But like I said, I'm not interested in these metrics. Just focusing on the linear algebra. So this is where if you haven't done this before, this is all you need up to this point. And then this confusion matrix, it will have run LDA and will give you the confusion matrix. So if you have a little more courage, you can go further and do this one for plotting the first component. So if doing only fitting, if you want to get the new components, you have to transform, right? You have to transform the data. Remember the first one earlier, it was just fitting the data and then predicting. But if you want to plot now in the new transformed space, you need to transform the data. Then I extract the components and then plot them after transforming. So you can actually print this to see what it looks like after transforming. So this will give you transformed data. That transformed means projected into the new space that maximizes the separation. Then you're able to plot it in the new transformed space and you can see the separation. But here we plot it only in the first dimension. We don't bother with the second dimension, just the first dimension. I think R has a direct way of plotting this. That have a direct way of plotting this. You don't have to struggle too hard to write all this. In R, it can be done in a few lines. If you want to use R. It can actually give you these histograms. Are there any questions? I think we can now stop there.